Thank you for sharing that with me today. My name is Anthony, and I'm a PhD student here at UVic. I play in the energy modeling space, and today I was hoping to talk a bit about open source energy modeling tools. Okay, so the contents of this presentation, I'm going to start out by laying out the intent of the presentation so we all know the point I'm trying to get at. We're going to talk a bit about an energy modeling pipeline. So when I'm doing energy modeling, this is sort of the framework I have in mind when I'm doing it. So to share that idea with you guys. Then I'm going to look at some industry standard tools, specifically a sampling of tools and where they fit into this pipeline framework. I'm then going to swap out those tools for some open source alternatives that I've been looking at. And then the main event will be focusing on some example applications. So I put together 2 example applications showing how you can drive this pipeline using entirely open source tools. And then I'll talk a bit about my future work. This presentation is Creative Commons. It's publicly available, and all of the examples I'm going to show, all of the code, all of the data, all of the docs, that's all publicly available. It's all on GitLab. So you guys can take that home with you afterwards if you like. So the intent. First of all, I'm going to introduce an energy modeling pipeline. Then I'm going to quickly touch on those industry standard tools to see where they fit into the pipeline. And then I'm going to tour the open source alternatives and then focus on 2 example applications. So the slide is kind of repeating what I already said. All right, energy modeling pipeline. So when I think of energy modeling, a framework like this is what comes to mind. So if you look, the little cylindrical guys, those are data sets. And then the square parts are modules or pieces of software that do a specific job. So if I want to model, say, the integration of renewables and storage into a community, the pipeline doesn't start down here. It starts up at the data and the supply and demand side. So I have to understand what the demand that I'm trying to meet is, and what all the different components of that demand are. And then I have to understand the supply side as well. So things like solar and wind assets, how are they going to behave given the environmental data that I've pulled? So that's the pipeline I have in mind. And then where do these industry standard tools fit in? So when I'm looking at the pipeline, there's a number of tools that come to mind. So if I'm looking at the demand side and I'm looking at the buildings demand module, one option that comes to mind is RedScreen. I think Energy Plus has also been mentioned. I think Martha mentioned it in her presentation. There's a lot of options. RedScreen is the one that came to mind. If we're trying to model vehicles demand, there is a package in MATLAB called Autonomy that's been around for a while that handles the load profiles of electric vehicles. On the supply side, if you're doing modeling in solar and you're using industry standard tools, it's a pretty good bet that you're using Helioscope, if you've heard of it. It's a fairly well-established tool for solar. And then for wind, there's WASP, for example. And then on the integration side, we've heard Homer be mentioned a couple of times today already. That's standard for microgrid modeling. If you're moving up to more wider area networks, then you might start to see something more like Siemens PSS pop up for that type of modeling. And these tools they're well entrenched. The RedScreen is the world's leading software, and Autonomy is used by a ton of people. And Siemens is saying that 70% of world electricity consumption flows through infrastructure planned or analyzed by PSS. So they're quite impactful tools that are used by a lot of people in industry. The main catch, though, can be the cost, which has been mentioned a couple of times today already. So if you're a very large company, maybe it's not a big deal. But if you are a smaller player, these licensing fees can add up really fast. We've already mentioned that Homer can be rather expensive. I tried to find pricing for Siemens PSS, but their very lovely, beautiful website gave me the impression of if you have to ask, you can't afford it. So it's quite expensive. Yeah, so that's industry standard tools. I had some other thoughts on those. Industry standard tools, they tend to be closed source. It's proprietary IP. The company is protecting their IP. That's their trade secret. That's what they make their money with. So it's understandable, of course. But there's a couple of drawbacks to that. On the engineering side, engineers, we need to understand the tools that we're using. And if the tools are closed source, then you're relying on the documentation, and the documentation isn't always great. nor does it always keep up to date with the software itself. Just because the docs say it's doing one thing, the actual software may be doing something else because they haven't updated the documentation yet. Also not great for research quality or transparency. Good research should be well understood and reproducible, and closed source tools don't always let you do that. The tools are largely siloed. If you remember that modeling pipeline framework that I showed, there's a lot of interaction between the different components, and each component has its own tool, like the right tool for the right job. The tools don't always talk to each other well. That's usually up to the person using the tools to translate the outputs from tool A to put them into tool B to achieve that flow of the pipeline. There's some exceptions to that. Like, for example, Helioscope, you can take output files from Helioscope and then Homer will accept them as inputs. So somebody has implemented that interoperability at some point. But for the most part, the tools are siloed, and them being able to work with each other is not really a design consideration. Also, n different tools means learning n different interfaces, which can increase the learning curve. So then what about open source tools? What can we do about this? Well, here are some examples that I found when I was looking for alternatives to the industry standard tools that I showed before. And you'll notice that they're all in Python. So if you know Python, you can use any one of these tools, which is a nice thing. You only have to learn one interface. But yeah, for the buildings demand side, there's two tools that work nicely together. There's Demand Ninja and Ramp Demand. For vehicles, there's Ramp Mobility. So the same dev team that does Ramp Demand. On the data side, there is a tool that lets you pull data from the European Center for Medium Range Weather Forecasting, which is a really good data set to pull from. And then GC and Wind Power Lib for solar and wind. And then PGM for microgrid. And there was another tool I came across called Calliope that can do wider area networks. So it actually does routing energy through the network topology, which PGM doesn't do, being a microgrid model. So Calliope is another one that I'm interested in taking a closer look at. Just a quick overview of each of the tools. CDS API, you can use that for pulling data from the European Center for Medium Range Weather Forecasts. The data has a pretty good license, so it's Creative Commons attribution. And the reason why I bring that up is because the data license is commercial permissive. So if you are using the data and you're doing a for-profit project, that's fine. So that's one thing you need to keep in mind, is the licensing. And yeah, there's the QR code for it there. I'm not going to dwell on these. I'm not going to dwell on these too much because I want to get to the examples. Demand Ninja, that handles the modeling of heating and cooling loads, but it doesn't handle appliances, whereas Ramp Demand does handle appliances, but not heating and cooling loads. So putting those two tools together is how I was able to do the building energy modeling. Ramp Mobility handles electric vehicle charging loads. I didn't play with this for this presentation, so I don't know too much about it, but the same team that made Ramp Demand made this tool. The Global Solar Energy Estimator, so that's what GC stands for. This is built on top of an older Python library that does solar PV modeling in quite a lot of detail. And this tool works well, so I'm definitely going to be working with this more moving forward. Wind Power Lib, that is a project that was spun off of Feed-In Library. Feed-In Library was a tool for modeling the feed-in of different renewables into the grid overall. And then this package was made with a focus on the details of wind energy. PGM, which I wrote, it does integration modeling and supply-side modeling, but not network routing. So this is a microgrid model. And then Calliope is a network integration model, which, yeah, is interesting. So I need to take a closer look at this one. Haven't had a chance yet. Some other thoughts on open source. Open source software is open, so it can be understood. If there's something in the documentation that isn't clear, you can always look at the source code to understand exactly how the model is working. It's also flexible. We've seen a couple of examples of that today already. It can be made to do whatever you need it to do. And that openness and flexibility facilitates easier interoperability. It's also better for collaboration between different researchers. We can all work together using the same language and the same tool. Where it does tend to suffer is on this industry standard piece. So the industry standard tools are well established. There's a lot of user confidence in these tools. So one question that I'm working through is how can open source software be made to deliver the same user confidence as the industry standards? Because that's really important for its uptake and also for its quality and reliability. Okay, so some example applications. So I worked through some example problems of actually using these open source tools to drive the modeling pipeline. And I'll show you the kinds of results I was getting. So again, everything that I'm showing here has been shared publicly. So if you want to pick up these scripts and play with them yourself or fix whatever I got wrong, they're all there. And I can share the link in plain text format later if you'd like it. For these examples, I'm going to focus on this scope. So I'm going to start with pulling data from the ERA5 database. And then I'm going to do building energy demand. And then I'm going to do solar and wind production. And then finally, all that will feed into the integration modeling that I'm doing with PGM. So for this example, just think of a community of 40 residential homes. So we're just building a little residential neighborhood is all we're doing. Modeling the appliance loads, I'm getting something that looks like this for a year. And those are the different appliances that are in play here. So in hindsight, I would go back and model this day to day rather than the whole year in one shot. But modeling it in a single year, this is the result I got. So for all 40 homes, it's upwards of about 85 kilowatts is the appliance load. And the two examples that I'm thinking of, so we're building these 40 homes in two different places. The first example, we're going to build them around Bella Bella. The appliance load is electric, and then the heating and cooling loads are going to be satisfied by air source heat pumps. And then we're going to do a similar exercise in Cape Perry. The appliance load, again, is electric. The cooling load in the summer is air source heat pumps, and the heating load in the winter is supplied by a district heating system. So that'll be a combination of diesel waste heat, hydrogen, and just diesel boiler. So for Bella Bella, I went and pulled some data from the ERA5 database, and this is an example of some of the data features I got. So the plot on the left, that's the air temperature for this location over the course of a year. So other than the cold snap in January, it's between about 0 and 20 degrees Celsius throughout the year. The middle plot is a time series of the solar resource. So that's global horizontal irradiance. And then the plot on the right is the wind speed at 10 meters elevation. So the modeled heating and cooling demand, this is from the Demand Ninja tool, and this is per home. So in the top left, there is the same temperature time series as I showed on the previous slide. So that's just the air temperature outside the house. And then you can see the cooling and heating set points that I used. So I'm saying that heating kicks in at 18 degrees. Sorry, heating cuts out at 18 degrees and cooling cuts in at 22 degrees. So for this location, it's 3,400 heating degree days per year. The bottom left plot shows what's called the building adjusted interior temperature. Essentially, that's what the thermostat feels if there's no active heating or cooling. So that's the signal that actually drives whether you have heating or cooling load. And then the plots on the right, the top one is the heating load, the bottom one is the cooling load for a year. So the modeled total demand for this example, the top left, you can see the complete electrical demand time series. Bottom left is its duration curve, and then on the right is just the total energy demanded over the course of the year by category. The modeled solar capacity here, so this is the capacity factor of the solar at every hour over the year. And then the plot on the right is showing its duration curve. And then the same for wind power. So the plot on the left is the wind turbine's capacity factor, and then on the right is its duration curve. So now to the integration piece. So if we power this community using only diesel generators, so we have a diesel generating plant that looks like this, you can see the capacities of each asset around the circumference. That's showing where the energy is coming from to satisfy the entire annual demand. And the fuel consumption for this is 273,000 liters per year. So then what happens if we integrate wind and solar and battery storage? So I decided to integrate 325 kilowatts each of solar and wind. So that's about 1.5 times the maximum load or the peak annual load. And then there's a lithium ion battery. Power capacity is set to the max load, and the energy capacity is 2 hours of peak load autonomy. So if we build a system like this, it's showing that that we're getting about 41% diesel displacement. So we're using about 41% less fuel in this case. For example, 2 for Cape Perry. So again, here are the resource data sets, or the climate and weather data sets. On the left is the air temperature, so it gets cold. The middle plot I thought was interesting because of the latitude we're at. You can see it's quite dark in the winter, and then we have this midnight sun effect in the summer. I just thought it was kind of cool to see that and coming out in the data. And then on the right is the wind speed at 10 meters elevation. Here's our heating and cooling demand. Bella Bella was about 3,400 heat degree days. This location is more like 10,000, so it's quite a bit more of a heating load. And in the summer, interestingly, there's a lot more cooling load too, because the sun being up all the time, solar gains in your buildings, there's a cooling load associated with that. And these are the model results I'm getting for that. So the modeled total demand here, on the left, that's just electricity. On the right, it's everything. So we can see the appliance and cooling demand. For this example, that's being taken to be electric. The heating demand is not. That'll be satisfied by the district heating system, but it is the heating load is the lion's share of the total annual demand. The modeled solar capacity. So again, it's dark in the winter. We don't get much then. But at other points in the year, this is what the solar panels are doing. And the wind production is shown here. So what kind of district heating system did I want to model? This is what I had in mind. So we have our 40 homes. The red and the blue lines are hot supply and cold return lines, respectively, of some fluid. And then there's 3 heat exchangers in play here. The primary heat exchanger on the bottom, this is recycling waste heat from the diesel generating station. Then there's a second stage that is a hydrogen-fueled boiler. So the idea here is that excess production from our solar and our wind, if we can't store it in the battery, then it's sent to the electrolyzer and it's used to make hydrogen. And then lastly, we draw diesel from the same tank that the generators draw from to run a diesel boiler. So if we need to supplement our heating supply, we can do it that way. So when I model that, on the left side is just electrical, on the right side is just heating. So on the left side, again, we have just diesel generators. So this is our base case. And to satisfy the electrical, it's about 128,000 liters per year. And then on the heating side, the waste heat from the diesel generators can do about 1/3 of the annual demand. And then the rest is topped up with diesel heat. So that results in consuming another 116,000 liters per year. So then what happens if we integrate renewables into here? So we're building out solar and wind, and these are quite oversized relative to the electrical load. So they're driven more by the heating load. I set them to 1.5 times the peak heating load. And then where there's a lithium ion battery system, which is matched to the electrical load. And then we have a hydrogen system. There's no fuel cell, so it's not doing anything electric. It's just making hydrogen for heating. So on the electrical side, we've displaced about 51% of the diesel, which is good. The double-edged sword there, which I think Martha mentioned in her presentation too, is that there's also now less waste heat to work with. So we have to make up the difference with other heating sources. The hydrogen in this case can do, looks like almost half of the annual heating demand, with the rest being made up by diesel. So the result on the fuel side looks like about a 44% reduction in fuel consumption. And that's the time series of heating for this one, because I thought it was interesting to look at. So on the left is the base case where we have only diesels. And then on the right side is where we have this system that includes the electrolyzer. So at what points of the year is hydrogen available? Most of it is in the late summer, early fall, because you have all summer to bank it up with the excess solar and wind production is what I'm finding. So seems to make sense. Okay, so future work. This energy modeling pipeline, these examples I put together were a good exercise, but I want to do more. I want to work on curating tools and developing them further and sort of standardizing the whole package. As part of my work, I'm hoping to apply this to all of Vancouver Island. So I would like to be able to scale up to that level of modeling. I mentioned the question of user confidence in open source software. That's a question I want to try and address. And then the last point is, does that question overlap with the notion of research quality code? So what does it mean for a piece of software to be research quality? Is another question I want to address in the course of my work. And that's it for me. Questions? Hi.
Hi. Yeah, I'm curious if you've tested the results of the open source options against more traditional sources, like maybe from the open, out of the box perspective on the open stuff.
What, you mean like compare them to the industry standard stuff? No, I haven't.
I did compare my model results from PG. Got comparable electricity model results. 0.4% off this. So yeah, I did some validation.
Awesome, thank you. I should caveat my no. It's because I don't have a license.
Yeah.
I don't have a license for this software, and I am not paying for it.
There's a free trial.
Free trial? Okay.
21 days.
PSS now Siemens is having education so it's good time to probably plan things.
Okay. Hi.
I just want to commend your work because, yeah, even as a higher education institution, 3 ETAP licenses cost us $180K. So it's not cheap stuff. I guess I have one question and a comment. I guess the question is, what is your benchmark for industry standard or research rigor? Like, how do you define that? How do you say yes, we've achieved it, or no, we haven't?
Yeah, that is one of the questions I want to address because I don't really know. Like, what is the question of user confidence? I guess industry standard could be defined as the degree of user confidence it provides. So I kind of flip that on its head. And then the notion of research quality is quite squishy. I don't know exactly what that means. So I don't know. I have to look at that more.
And then I guess the second question, sorry, don't mind.
No, I'm sorry. I was just gonna kind of begin on that. Like Sophie did that validation between Homer and PGM because like we were interested, like we want to replace Homer with open source software, but we're not, we don't know. We're not confident enough in that to know that. So that's why we wanted that as like our sponsored research project. Also we did something similar with Open DSS. And I guess it's compared against ETAP, like we're going through the connection impact assessment with QEC on one of our projects. So like the contractor's taking too long, we know they're using ETAP or something. Let's try and do our own model in Open DSS and compare it so we can, if the utility comes back and tells us we have to do all this stuff and invest in all these things, we have a sense where we can push back. But I'll say we matched their results with very little input, I think, as well. But I think it was also the contractors also had little input. We're like, how did they come up with these assumptions? It turns out they were just making us, like Casey hadn't shared that data with them either. So we're all just making the same assumptions. But I don't know, maybe that's again like where the universities can partner with industry is like hoping to benchmark this more or partner with utilities, because like, yeah, $180,000 on software. If you can get the same results from something open source that we were able to figure out kind of like in a month, like that is pretty worth it.
Yeah, I know. I definitely agree there.
I also, I did it twice, like I did it when I was went through Chesterfield Inlet that made it into their community energy plan. It was mutually beneficial because I got to validate my results again, but also I validated their results, like no hydrogen. So I did it twice, and it was super good learning experience for I think the consultant BlackRock role on my side. I learned a lot from that experience. Communicating of like, I had to understand all of the model inputs that it up because I had to directly do that comparison. So yeah, I think it's a really good exercise to link academic studies for having as we get more source tools. Let's test them while we're running our homework results and see where they
I just comment on that. I would caution against looking at any one platform as accurate. So if we get the same thing as Homer, therefore we're doing it correct. Don't think that Homer is correct. It's just kind of a socially accepted best standard that we have. But this could get better results than Homer. So it could, depending on how you model it, depending on how you implement the algorithms. So don't think if you are wrong or off of Homer that you are necessarily wrong or bad. You go down.
Yeah, I mean, if one tool is open, the other is closed, you're comparing them. Is it really apples to apples? Because the other one's closed. Like, you can't really know.
I guess a follow-up question or comment. So when we developed our MATLAB toolbox, we were actually initially thinking of like, hey, sharing this with everybody as much as we can. But then when we got down into the nitty-gritty, it was very much then we would become we become software service organization as opposed to a project, support. I was just wondering if how, I guess making it open source, you could say, hey, it's not my problem anymore. Other people could add to it, but how are you managing that as opposed to you being a help center?
Well, you're right. The way one of the key pieces in that is the licensing. So the terms of the licensing. Most open source licenses contain wording to the effect of this code's released as is, no liability, best effort. In terms of responding to support requests, that could actually become part of a funding stream. So if you want technical support or you want to make a feature request or something, yes, but you have to be a sponsor of the code in order to make that kind of a request. Otherwise, it's open source and it's released into the public under the terms of the license. So I'm not nervous at all. Hi.
I took a quick overview. I think it's through like Demi or something on wind power lift, and I haven't had the chance to actually use it in a real world setting yet. But I was wondering if you had. It seems like a pretty robust and flexible tool, just going through it. And I was wondering if you had an opinion on how robust.
Well, I will be honest. This is the first time I've used it, but from a developer point of view, looking at the repository and how things are organized and how the code was written and the documentation and everything. This tool it's available in the Python package index, so you can just pip install it, which is always a good sign because professional projects are usually available on PyPI. The documentation for this one was quite good. So picking this up for the first time, reading the docs and going, oh, okay, I get it. And away I go. I could do that. You can't always do that with open source projects. If the documentation's not good, then it's much harder to start with it. An open source project lives and dies by its documentation. So if the documentation's not there, it's pretty much dead. The documentation for this one is really good. And then the last piece I usually look for is, does the repository include a testing suite? So there's an automated testing suite. And the reason why that's there is if I want to make changes to the code, I need to be able to verify that I haven't broken something else. So there's this test suite that I can always run every time I make a change to make sure that everything's working the way it's supposed to. The fact that all of those elements are present in the repository gives me confidence as a user that the developers who build this aren't a bunch of Muppets. Like they know what they're doing, they're writing good quality code. So kind of a backwards answer to your question, but based on my initial interaction with WinPowerLib, I'm satisfied.
Me too.
Back.
You had mentioned in the beginning over costs and part of the integration pipeline. Are you aware of any databases that
For cost specifically?
I didn't see it as a cylinder?
Yeah, I mean, so costs, where would I stick that? I mean, model is subject to revision, obviously. I reserve the right to be wrong, etc. Economics. I would probably batch economics in with, probably not the best place to put it, tech data, but basically this is the data set that informs these bits on how they should be running. So if economics is part of it, then yeah, economics is a big deal, so it should probably be its own data set. In terms of data sources, I mean, other than the obvious like StatsCan or whatever, I don't really know, honestly. So another opportunity for some interdisciplinary stuff because I'm not an economist and I don't want to be an economist.
Modeling the cost is always it depends on the location and everything. So it changes. So you have to think on general values for this, so you don't get a certain type of definite numbers to put in the model. But then if you are running it for a specific location or something, you obviously need to change those numbers. And it would always be different for different places.
Yeah, of course. Awesome.
Right. You said you haven't like started engaging industry with this tool. Have you thought of anyone?
Engaging, well,
Like
I haven't really thought of it because I'm kind of just focused on building the tool, and I definitely see the value in talking to industry players and doing that. But so far, no, I haven't really reached out. Other than the different groups here that have used it before, that's all the industry uptake that I'm aware of.
I guess I'll just, there is a version of the PGM that is existing right now. And there's also a Slack channel. And even though there's no like funding to maintain it, he does answer within hours. Very good answering questions. I do encourage people to look up because it's that will feedback that will go into the next grade.
Yeah, that's a good point. I didn't think of the Slack channel, honestly.
Yeah.
What's the channel?
It's just a channel on Slack. I'd have to send you a URL for it.
The link is for the Slack channel also on the
Yeah, if you go to the GitHub for PGM, the link for the Slack is on there, so anyone can join it.
and there's like YouTube. So that's
And it's basically why you could change if you want to have Soviet provided. My thought is that if you want to have hydrogen, you can have oxygen. So it's basically the DIY yourself on
Yep.
stable.
That's the beauty of open source.
and
Yeah, back in the back.
One more thought. I just wanted to give you a quick plug for some of the interface that the game modeling that you've done. With megawatts.
Yep.
I think.
Megawatts and marbles, yeah.
Sorry, megawatts. Imagining an interface for this at some point that's not code based.
Oh, for this?
Yeah.
Yeah, no, I'm thinking of maybe it's like who here was using computers back in the 90s? You guys remember the concept of a wizard? It's like, oh, this is a wizard for this program, and it takes you through basically a series of checklists to set it up and run it the way you want. Something like that is not hard to build, and that's something that I was thinking of layering over top of this, so that you don't have to be up to your elbows in Python code to use it. You can use just a graphical interface if that's more your speed. Yeah, and there's definitely a lot of value in doing that because that opens it up and makes it a lot more accessible to a lot more people. So yes, definitely going to be doing
I'm
that.
also imagining from earlier conversations like that gap in training, and if there's local uptake and participatory modeling that's happening, having that kind of ability to visualize it and see.
I see what you're saying.
See the
Yeah.
connection between the pieces, and
yeah,
it could become a training tool that can improve the model.
Yeah, definitely.
And I know you have the talent to do something.
Thank you. Well, I'm done classes this term, and starting in the new year, this is going to be my focus. So bring it on.
Drop it in the Slack channel.
Hmm?
Drop it in the Slack channel.
Please don't blow up the Slack channel. There's only one of me. Anything else? Hi.
Question. So, how many academic researchers use outside
So yeah, I don't know.
what situations workshop on academic researchers? So, one of the main reasons for user confidence in listing software is because of people using it for longer periods of time. So, user interface is definitely an advantage to get started, but just practice.
Yeah. Yeah. Maybe for a future workshop. A good idea. Hello.
I just want to support his argument because coming from industry, one of the issues we run into is we're applying for funding from organizations like Hydro. They typically have a list of your stuff that you could have used usability study.
Yeah.
Obviously, PGM's not on
No,
the list.
it's not.
It sounds like it would be great to get that on the list.
Yeah, and that goes back to the user confidence question.
Yeah.
I need to be able to answer that question. So yeah.
Basically, the project is validators.
But I think it's a matter of going through usability studies and examples with people like BC Hydro and showing them that actually this works, and then eventually their engineers will say, "Oh yeah, we'll add this one to the list because we have confidence."
Yeah, it's a good point. Might be a good discussion to have with Wes.
Well, I think Wes, you have already been some showers.
Oh yeah,
looking at your modeling. So
yeah, and it's Wes made some good contributions along the way. The whole "it's open" challenge and it gets better. There was definitely some challenges from Wes that helped make it better. So that was a good interaction. Okay, well, thank you.